All right, here we are for AP Physics pendulum problems. I'm going to take a look at problem 1 here. It says a simple pendulum has a mass of 0.25 kilograms and a length of 1 meter. It is displaced through an angle of 15 degrees and then released. They want to know the maximum speed, the maximum angular acceleration, and the maximum restoring force for that pendulum. All right, so I'm going to work this on some paper as usual. There we go. So I've got my pendulum. And I know I'm exaggerating the angle here, but 15 degrees is the what it's displaced through. So that is like its maximum displacement. Okay. It's going to oscillate back and forth, right? I did not do a great job drawing that. Sorry about that. You get the idea. There we go. Let's see here. They told us that the mass is 1/4 of a kilogram. And they told us that the length is 1 meter. And that's it. They want to know the maximum speed. So we could do this with energy. Yes, we could. Is that the way I want to do it? Sure, why not? I wish I had drawn this a little bit more nicely now, but, you know, them's the breaks. This looks familiar to you, I think, from the circular motion unit. You say, hey, if I know this whole thing here is L, then this whole length is L. But what's this bit? Well, I know that this bit here, see that right angle, that right triangle, hypotenuse L, this is the adjacent to the 15. So this length is going to be L cosine 15. And so what's this bit? The height difference there. That height difference, when it swings down, it's going to go down L minus L cosine 15. Make sense? That's ugly. L minus L cosine 15 is that height change. And so I know that as I swing from there to there, I'm going to lose mgh. I'm going to gain 1/2 mv squared. You know what I mean? As I'm going from rest here. Do I need to show out all that whole energy, conservation of energy argument? Oh, what the heck. Sigma W is delta K plus delta. I'm going to make my system be the pendulum bob and the Earth. That means I can have a delta UG. All right. I'm going to treat this as translation 1/2 mv squared. So when I do this, I'm going to go from, let's go from rest here, or release it, and to this position, the equilibrium position. So when I do that, there's the only outside force acting on the pendulum bob here is this, the tension, the string. But that's perpendicular to the motion at all points, so it does no work. I'm going to have that kinetic energy there at the bottom, which is where minus the start, we release it from rest. And then delta UG, that's going to be my mgh final minus my mgh initial. Let's call we want to call the final height 0? Yeah. Minus my initial height, L minus L cosine 15. So mgh, well, let's just say UG initial. There we go. So rearranging this, you're like, yeah, look, the UG initial equals the K final, right? Potential energy turning into kinetic as we swing downward. My initial potential energy is going to be mgh naught, 1/2 mv final squared, right? And again, we are trying to find that max speed when we're at the bottom there of the swing. Mass. I'm going to get root of 2g h naught. It's supposed to be a root, sorry. Is that v at the bottom of the swing, which is my max v. That's going to be the root of 2g times L minus L cosine 15. So that's going to be the root of 2 times 9.8 times the quantity 1 minus 1 times cosine 15. One minus the cosine of 15 is going to be that times 9.8 times 2. Take square root of that whole mess, and I get 4.35 about. 4.351 meters per second for my max speed. All right. Hey, when I was working this, all the physics is right, but when I got to this step, so you have that L minus L cosine 15, and the L is 1 meter, so I got 1 minus 1 times the cosine of 15. The problem is when I punched it in my calculator, I actually accidentally hit times instead of minus. So let me just fix this value here. Okay, so it's going to be, what do we got here? 2 times 9.8 times the quantity 1 minus cosine 15. Then we want to take a square root of that. And I get 0.817 meters per second. Okay, so that's 0.817 meters per second. Okay, not 4.35. Okay, all right. All right. Let's see. They also want to know the maximum angular acceleration. And you say, well, angular acceleration. I'm going to use I think I'm going to use A as R alpha for this, okay? And you say, I'm going to have the maximum angular acceleration, though. You know what? I'm not even going to use that. I'm not even going to use that. I'm going to use, I think I'm going to do this. So the torque is I alpha. Yeah. Let's do this. And we're going to have this. I isn't changing. Our moment of inertia isn't changing. It's the same physical system. It's this simple pendulum. So we're going to treat the mass like a point mass at that distance from the axis. So I know that my I is the sum of the mr squareds. You know what I mean? That's what I use for point particles. You say, but this is just one particle, one mass of a fourth at a distance from the axis of rotation here of the length of the string, 1 meter, right? So, whatever. So that's just a fourth. Now the torque, the tension exerts no twist. The only torque on the system here is from gravitational force straight down. My R vector starts at the axis of rotation and goes to the point where the force is acting. So it's going to continue going in this direction. Hey, that angle with the vertical is 15. That angle with the vertical is 15. So when I do my R cross F, my R is 1 meter, right, for the length of the string. And then my F is just mg. And then sine theta is sine of the angle between the way R is going and the way the force is going is sine 15. So that torque is going to be, again, we're doing R cross F. And so that's going to be 1 times the force, which is mg. I'll write it out variables first, sorry. Rmg sine theta. Sorry. So that's going to be 1 times, that's an R, in case you're wondering. 1 times mass of a fourth times 9.8 times the sine of 15 is 1/4 alpha. We can cancel that fourth. So my alpha is going to be 9.8 sine 15. My calculator says that's 2.54 about radians per second squared. Okay, that's part B. And then part C, they want to know what's the maximum restoring force. You say, well, now what they mean by that is the force that tries to push you back to equilibrium. In this picture then, the part bringing you back to equilibrium is the part tangent to the curve, right? That's the part that's trying to push it back to equilibrium. So I believe that what they want here is going to be for us to take that gravity force and split it up into perpendicular to the path and parallel to the path. Components, I think this component is what they want. That would be mg sine 15. So I think that's what they're after in part C. I'm going to put part C up here. The restoring force is going to be biggest, right, when this angle is the biggest. But when it's swung all the way back, that's where the biggest part of gravity is going to be tangent. When I get down to here, there is no tangential gravitational force. The gravitational force is straight up and down. So the acceleration would be the smallest there. It's going to be the biggest there when it's extreme. And so you say, hey, that maximum acceleration or maximum restoring force, we say that's just going to be mg sine 15. So that'll be 4 times 9.8 times the sine of 15. And I got 0.634 newtons for that max force. All right, that is problem 1.